All right, here we go. We are now starting beam design. Probably the most complex topic in this course. In my opinion, one of the more interesting ones too, because we are now actually going to be determining what size beam we need for a building. Like this is, I promise you, what engineers actually do in the field. Of course, they'll have like better software to help them with the process, but what we're doing right now is real world examples. So, this is how you design a beam. When you design a beam, you are checking to make sure that it can safely support the design loads. So, you want to figure out what's going to make the beam fail. So, you're going to figure out which beam you need that could support all the possibilities of how the beam would fail. So beams are designed to be able to handle bending moment and shear. Do those sound familiar from what we did about a few weeks ago? They should. This is where the moment and shear diagrams come into play. So that's two ways of failing. The last way of failing is deflection. Deflection is when the beam gets loaded and bends, that gap right there is how much it's deflecting. And of course, we would like to minimize how much material we are using. So we don't want to over design something. If we make a beam really big and much stronger than what we need to, we're actually wasting material and money. So we want to design a structure that could safely support the load with the minimum amount of material possible. So we are trying to protect our client that way. So now let's get ready to design a beam. We will check again 3 things on sizing a beam. First, we are checking the moment. We are making sure that the moment applied to the beam loading could be handled by the beam that we choose. We are also going to check for shear failure. We are going to check for deflection. And then you're also going to be doing them in this order. So here are the steps involved in designing and sizing a beam. What is a beam? Well, a beam is going to be like those I-beam structures. And by designing or sizing them, we are going to be determining like the geometry of it. Like, is it going to be 10 inches wide, 12 inches, 13, 14? How big of a beam we need? Just wanted to establish that. Okay, so the steps involved are as follows. Step 1, establish the design loads. So you know what your building is going to be, geometry wise. I know it's going to be maybe a 10-foot by 20-foot building, and it's going to be used for, I don't know, a bank or something. So we know what the loads are. That's the dead and the live load. Next, we're going to analyze the beam. After we analyze the beam, we're going to select a preliminary member. We're going to guess first. And then once we guess, we're going to check that beam. And if it works, great. If it does not work, we're going to repeat the process with a different beam to achieve a safe and efficient design. And then we will take it from there. So let's go through them again quickly. Establish the beam design loads. Hey, we actually already did that. That was when we figured out the dead and the live load and the tributary width and the tributary area. Analyze the beam. We already did that. That's when we calculated the max moment and max shear. So those 2 steps are done. Now we're going to choose the member. So you cannot just look at a max moment and a max shear and then immediately know which size member beam you need. It doesn't work that way. In fact, there's no way to just look at what your max moment and your max shear is and know right away which beam to choose. Instead, you have to just guess. And you'll pick logical guesses, but I'm going to pick a beam and then I'm going to analyze it. And then if it doesn't work, I know I need to choose a bigger one. And if it does work, well, maybe I can choose a smaller one that's a little bit more efficient. And you're going to be doing it a few times until you get the one that works and is both safe and efficient. That's called an iteration, an iterative process where you keep repeating the process and then you're converging to the best optimal solution. Okay, So I want to introduce something called ASD, Allowable Strength Design. ASD is a method that engineers in the field use to design beams. The other method is called LFRD. It's like load factoring, I forget. ASD states that the beam's overall strength is essentially the maximum stress it can handle. So we're equating strength to the amount of stress that it can support. So the strength of steel is the yield stress. I need you to get that concept. Remember those stress and strain graphs last video where you wanted to be under the yield stress to be in the elastic region? That's where this comes into play. We're saying that the strength of steel is its yield stress. And that'll be given to you. Remember, if I'm telling you it's A36 steel, you know 36 KSI is the strength, so on and so forth. And then the beam's strength must exceed the amount of stress exerted. And that makes logical sense, right? If the beam can only handle 36 KSI and I apply 40, you're going to have a bad day. So you have to apply less stress than what it can handle. So ASD takes the actual moment and shear a beam will see from an applied load and then multiplies it by a factor of safety. So what that means is if I analyze a beam by doing the moment and shear diagrams and I find the maximum moment to be like 100 kip feet, I'm going to multiply it by a factor of safety to make it even bigger, and then that's the number I'm going to be designing my beam to. That's kind of how we can be conservative with it. Okay. So we say that strength is related to stress, and the strength of a material is the yield stress. And yield stress, again, will be given based on the material. And then ASD limits the maximum internal forces by using factors of safety. We say that the nominal strength is the actual strength we will use. This is a lot of terms and definitions, so bear with me. Nominal strength is the actual strength we will use for the design. And then we have allowable strength, which is what it can actually handle. I like this slide more. I like this slide more than the last slide. This is a way of putting that into equation form. Okay. F of n is the nominal strength. Nominal strength is the actual strength we will use to design. This has to be greater than the internal force multiplied by the factor of safety. What am I talking about here? It's not complicated, guys. Not complicated. We are saying that the maximum moment, maximum shear, multiplied by a factor of safety is what we will use to design it to. So what are we using? We are using I-beams. I-beams are often called wide flanges. The flange is the little top part right here. So we might say that we have a W 12 by 58, and we'll get to what those numbers mean later. Why do we use I-beams? Well, I-shaped members are excellent choices for beams because they have a great strength to weight ratio, meaning that they're really, really strong for not as much material. They also have a high inertia. And if you're not familiar with what inertia is a measurement of an object's ability to resist change in position. And it's measured in inches to the fourth power. Kind of weird, right? And it is related to the object's weight and size. So the heavier someone is, the harder they are to push, right? They have a higher inertia. Also, depending on your shape, you're harder to move, right? If you're standing straight and tall and your hands are pointed right up in the air and then someone runs to tackle you, it's going to be easier to knock you down than if your arms are spread out. That's because your inertia is higher when your arms are spread out. Also, I-beams are strong when bent about the XX axis. So this is a little X right here, not sure if you can see it. But imagine that this beam right here was like 20 feet long, and then you were a giant. And you can imagine that it would be easier to bend it horizontally than vertically. Okay, so back to designing a beam. We must check 3 things when sizing a beam. Again, we did this already, right? Moment, shear, and deflection. Okay, here's the first one. Let's do this on the next video. And guys, I promise you, this is where, this slide here is where we're really picking it up. This is where this stuff, I believe, comes to like a head.